just I will give hint how to solve those problems. So, based on the theories that has delivered on today. So, coming to first problem, please go through the problem. For a steady 2-dimensional incompressible flow through a nozzle, the velocity field is given. That is only the x component of velocity is given, the y component of velocity is not given, although it is mentioned as 2-dimensional flow, where x is the distance along the axis of the nozzle from the inlet plane and L is the length of the nozzle. You have to find first one, the expression of the acceleration of the particle flowing through the nozzle along the axis of the nozzle, number 1, and number 2 is the time required for a fluid particle to travel from the inlet to the exit of the nozzle. So, first the velocity field is given as v equals to u naught 1 plus 2x by L I. Now, let us say this is the inlet to the nozzle, x equals to 0, this is exit to the nozzle, x equals to L. Let us say this is the x axis, let us say this is the y axis. Our first objective is to find the acceleration along the axis of the nozzle. So, you have already known that the given velocity field is steady. Now, what is about the acceleration? Let us say the acceleration along the axis of the nozzle. You know, for steady flow, if we write in general, this is del u del t plus u del x plus v del u del y. Since the flow is steady, so this term vanishes. Now, from the given velocity field, what is about the y component of velocity? So, it is not given, but if you look carefully, the x component of velocity, that is u equals to u naught 1 plus 2x by L. So, from the given velocity component along x directions, del u del y, that equals to 0. That means, this term also vanishes. That means, the acceleration along the axis of the nozzle is simply u del x. So, now if you substitute the x component of velocity and the del u del x, you will simply get the acceleration along the axis of the nozzle. That means, the first part, expression of the acceleration of a particle flowing through the nozzle along the axis of the nozzle, first part. Now, coming to the second part, I leave this as exercise to you, just find the final expression for acceleration. Now, coming to the second part, the time required for a fluid particle to travel from inlet to the exit of the nozzle. That means, it is given, the velocity field is given. So, it simply can be written as dx dt, that is u naught 1 plus 2x by L, or simply you can write dx 1 plus 2x by L, that equals to u naught dt. Now, if we integrate this from x equals to 0, that means the inlet to the nozzle, to x equals to L, that is the exit to the nozzle, and here t equals to 0 to to t equals to t, you will simply get what is the time required to flow a particle from inlet to exit to the nozzle. So, just do this and you will find what is the time required to travel a particle from inlet to the exit to the nozzle. Now, coming to the next problem, this problem is already done in the class, in the last class. So, coming to the third problem, a 3-dimensional velocity field is given, the 3 component of velocity is given. So, your objective to find 3, number 1 is the components of rotational velocity, the components of vorticity and the strain rates for the above velocity field. Strain rates means the linear strain rates as well as the angular strain rates as well as the volumetric strain rates. So, what is given? X component of velocity is given, x component of velocity is given as Cx plus 2 W naught y plus u naught. Similarly, y component of velocity is given Cy plus V naught, and z component of velocity is given minus 2 Cz plus W naught. These 3 are given. So, what is our objective? Our objective to find first the components of rotational velocity. Now, as you know from previous lectures, that is the velocity, rotational velocity can be written as half of curl of the velocity vector, that is simply half So, now if you write in component wise, that means if you write about x axis, this is half del W del y minus del V del z, about y axis and about z axis now just evaluate from the given velocity field this derivative. Just if you go through this, you will just I will solve one components and you solve the other 2 components. Half, what is about the this component, omega is not a function of y, so it becomes 0, and V again is not a function of z, so it 0. So, this is 0. So, just similar way you just calculate the other components of rotational velocity. Now, coming to the second part, as the components of the vorticity, as the you are already familiar, thus vorticity is just the twice of rotation, and means if you write the vorticity, is simply the curl of the velocity vector. So, in component wise if you write, this is x, that is nothing Now, just substitute the values of u, v and w and just you obtain the expression for the components of vorticity. So, I leave it also as an exercise problem. And coming to the last one, the strain rates for the above velocity field. So, strain rates, if we find the linear strain along the x axis, this is del u del x. Similarly, if you consider strain rate, linear strain rate along y axis, this is del v del y. Linear strain rate along the z x, this is del w del z. Just individually just find. If I write, this is simply c, this is also c, this is minus 2c from the velocity field. So, one more important, that is if you consider what is the volumetric strain rate, you have already familiar, the volumetric strain rate is nothing the sum of these three, and this becomes 0. Now, one more thing that you have to find, what is the rate of angular deformation, that is the epsilon x y, epsilon y z and z x. This is just del v del x plus del u del y, this is del w del y plus del v del z, and this is del u del z plus del w del x. Just substitute the given velocity fields and you will simply get the rate of shear deformation or angular deformation. Just solve, just substitute and finally you will solve. Now, coming to the last problem, in a 2-dimensional flow field, similar to the problem that has already solved by Professor Chakraborty, that in a 2-dimensional flow field, the fluid velocity components are given, x component and y component of velocity are given, similar to that u equals to ax and v equals to minus ay. First, you have to check that the whether flow is compressible or incompressible, and second one, whether the flow is rotational or irrotational. And then if the flow is incompressible, find the stream function, and another is if the flow is irrotational, find the velocity potential, whereas if the flow is rotational, then you have to find the vorticity. So, the x component of velocity is given and y component of velocity these two are given. X component is given as x minus 4y, whereas the y component of velocity is given as minus y minus 4x. So, by the time it is clearly shows that the flow is 2-dimensional. So, what is the condition for flow to be incompressible for 2-dimensional flow? You know that the divergence of velocity should be 0 if the flow is incompressible. That means del u del x plus del v del y, that should be 0. That means you first check that for the given velocity field whether del u del x plus del v del y equals to 0 or not. Now, if we check one, let us say del u del x, first del u del x, what is about del u del x? This is nothing 1. What is about del v del y? This is minus 1. That means the del u del x plus del v del y, that equals to 0. That means that it satisfies the condition for incompressible flow, continuity equation for incompressible flow. That means the flow is incompressible. This is the number 1. And number 2, if you consider, if you to check that whether the flow is irrotational or rotational. So, you know the condition for irrotationality is the curl of velocity is 0. That means for the 2-dimensional flow field in xy plane, this is del v del x minus del u del y, that should be 0 if the flow is irrotational. So, for the given velocity field, please check what is about the del v del x minus del u del y. So, if I write del v del x, this is minus 4, del u del y, this is minus 4. So, if we substitute here, it becomes del v del x minus del u del y, that equals to 0. That physically means the flow is irrotational. That means the flow is incompressible as well as irrotational. Now, if you go through the problem statement, if the flow is incompressible, then find the stream function. Now, you are already familiar from the previous lecture that for 2-dimensional incompressible flow, you can define stream function such that u equals to del psi del y and v equals to minus del psi del x. So, the velocity component is given, one is x minus 4y, another is minus y minus 4x. So, I leave it as an exercise problem to find what is the value of psi, similar to the example already done in the previous lecture. This is number 1, and number 2, as the find the velocity potential if the flow is irrotational, and already mentioned that the flow is irrotational. So, how to get the velocity potential? So, you know that the velocity potential can be defined for irrotational flow, u equals to del phi del x and v equals to del phi del y. Again this equals to x minus 4y and this is minus y minus 4x. And similar to the previous problem that is already done in the previous lecture by Professor Chakraborty, you just obtain what is the expression for velocity potential. Fine, and I leave these two as an exercise problem. Just find what is the expression for stream function and what is the expression for velocity potential function for this velocity field. Fine. So, now we will take some questions. RCID 1255. You are not audible.
এইটা থেকে বলতে হবে তোমারটা তোমার কথা শুনতে পাচ্ছে না তোমার তো মাইক নেই
Sir, is it audible, sir?
Yes.
Sir, is it audible?
Yes, it is audible.
Sir, is it audible, sir?
Yes, it is audible.
Sir, my question is from the previous session. What is my question means? The previous session, sir is explaining about that particle movement in whether it is translation or it is creating a deformation like that. Was talking about that. He told for translation, if the particle moves in the flow, if the flow is purely translation means no relative velocity between particles like that he told, sir. But regarding deformation, he told that some relative velocity will be there. So due to that, the particle size will be changed or deformation will be there. Like
Particle size? No, it is not particle size. No, no, no. Particles are particles, right? I mean, particles in a fluid flow are conceptual entities which do not actually exist in practice. So, particles are point masses.
Yes, sir. Regarding that only I asked.
Particles are point masses.
Okay, sir. Whether shape or
It's about element, fluid element, not particle. Okay, thank you.
পার্টিকেল বলতে ভেবেছে ফ্লুইডের মধ্যে পার্টিকেল চলে গেছে।
1308.
Hello.
Yeah.
Hello. Good
Yeah.
evening, sir.
Good evening.
Sir, actually my question is, in the Lagrangian approach and Euler approach, we consider in Lagrangian approach about your initial part means x0, y0, z0 and the time is t.
Yes.
But in Euler approach we consider x, y, z and t.
Yes.
So in both the cases if you see, so t is common. So why are you not considering about Lagrangian t0?
Okay, since this was taught by Professor Som, he will address this question.
Okay, sir. Thank you.
এটা তো বারবার ওকে বলা হয়েছে। হ্যালো হ্যালো
Please tell, sir.
Hello, do you hear me? Do you hear me?
Yes, sir, I hear you.
Now in Lagrangian approach you are correct that there is a T. What is Lagrangian approach? Here the particle history of particle of a given identity, the history is being monitored or is being found. That T is the time that a particle takes while flowing through the medium. This T is attached to the identity for a particle of fixed identity. You understand? And that identity is specified by its initial position. At t is equal to 0, the position is s0, that x0, y0, z0. And that time t is the time taken by the particle to flow from one point to other point, particle of given identity. Whereas in Eulerian approach when we take t, this t is the instantaneous time. You understand, where we fix a space coordinate and go on seeing the velocity and acceleration fields at different time. So what happens when the time changes? For example, we fix at a position velocity v1. Okay, that velocity v1 is the velocity of a particle which is there at that point at t is equal to t1. So now another time t2, the velocity is v2. So this velocity is of a different particle, not that particle has left, which has reached at that point at time t2. So this time is for a given point, so space wise for different points at different instant of time. You understand? Whereas in the Lagrangian approach, when we write the locus of a particular particle, the time is inherent with its motion. This time is the time taken for a identified particle. You understand the difference between these two times, but it is true mathematically. T is there in both the functions. You see the functions and go through my lecture, the physical concept behind it, you will understand the difference in T in these two cases. Okay? Thank you.
Thank you, I got the point, sir. Next question, sir.
Yes, please. It is from my
Good evening, sir.
Yes.
Hello.
Yes, please.
Sir, question is, sir, how can we differentiate incompressible fluid and incompressible flow?
I think I will give it to Professor Suman Chakraborty. He has already told incompressible flow. I also mentioned the difference, but let him explain. He has.
Okay, incompressible fluid, by that what we mean is that the density of a fluid, if it is virtually insensitive to change in pressure, So, the density could be a function of various parameters. Okay. So, if you have the density very weak function of pressure, then that kind of fluid is called as incompressible fluid. On the other hand, incompressible flow is a purely kinematic concept, it is not a concept related to fluid property. Incompressible flow means that if you have a volume element, there is no change in volume of the volume element, that means the rate of volumetric strain is 0. So, the rate of volumetric strain boils down to divergence of the velocity vector, or in a Cartesian, in terms of the Cartesian components, del u del x plus del v del y plus del w del z equal to 0. So, if that constant is satisfied, that means there is no rate of change of volume of the fluid element, the total derivative of the volume, the total derivative of the volume of the fluid element, then we say that it is incompressible flow. So, in terms of mathematical expression, it is 1 by volume into the total derivative of the volume, that is the rate of volumetric strain. The rate of volumetric strain is 0, that is the requirement for incompressible flow. So, incompressibility of a fluid talks about the fluid property, it does not talk about a kinematic constraint. Incompressibility of a flow, that talks about a kinematic constraint, that there is no volumetric deformation. So, that is the basic difference.
Thank you.
Okay. Thank you. 1 2 3 5.
Good evening, sir.
Good evening.
Good evening, sir.
Good evening.
Sir, I have two questions. My first question is, what is the physical signification of velocity potential function and stream function in fluid mechanics, and tell me some practical applications where it can be used.
Okay. So, we start with the stream function, because that was the first thing that we introduced. I clearly mentioned, but I am repeating again, that the difference between the value of the stream functions of 2 points represents the net volumetric flow per unit width across the 2 points. This is the physical significance. So, if you consider a streamline on which you consider any 2 arbitrary points, the values of the stream functions are same, and that implicitly proves that there is no flow across a streamline. Of course, explicitly by definition of a streamline, you know that there cannot be any flow across a streamline, but I mean this particular relationship between volume flow rate and the difference in stream function, from that also it can be shown that there cannot be any flow across a streamline. Now, velocity potential, like both stream function and velocity potential, what they try to do. So, if you see that when you look into the various equations, these equations contain the various velocity components u, v, w. This stream function and velocity potential try to express these velocity components in a parametric form, so that mathematically you reduce the number of variables. So, instead of having u, v, w as variables, you under some special circumstances you can use psi or phi as alternative variables, in terms of which the velocity components can be parametrized. Regarding the velocity potential as you can see is defined only for irrotational flow, and irrotational flow, of course, we will discuss in length about irrotational flow, we have a separate chapter altogether, but just to give you an idea that where irrotational flow is important, if you consider the flow close to a solid boundary, then close to the solid boundary viscous effects are important, but as you go further away from the solid boundary, there can be a region beyond which the viscous effects are not important. So, wherever viscous effects are not important, if the flow was originally irrotational, it will remain as irrotational, and if it remains as irrotational, it is possible to analyze the fluid flow without taking viscous effects into consideration. Now viscous effects, if those are taken into consideration, that adds to the complexity of the governing differential equations. We will discuss about the differential equations later on, but that adds to the complexity. So the complexity can be simplified to a large extent if viscous effects are not present. So we can divide the flow region into various parts, one part where the viscous effect may be important and another part where the viscous effect may not be important. The part where the viscous effect is not important, there the irrotational flow concept or the potential flow concept can be utilized. So these are some of the practical or physical significances of stream function and velocity potential.
Okay, sir. The second question is,
Okay.
what is the significance of vorticity?
Vorticity represents the rotationality in a flow, that is, if you keep a fluid element in a flow, then will the fluid element rotate or not, that depends on the vorticity. So if you know the velocity field and if you calculate the curl of the velocity field, and if the curl of the velocity field is a null vector, that means there is no rotationality in the flow. Vorticity has many important physical considerations, and vorticity is transported across the fluid by various mechanisms, and we will discuss about the mechanisms of transport of vorticity through fluid flow when we discuss about turbulent flow in one of our later chapters. Okay, thank you. 1064. Yeah, please be a little bit louder.
Hello.
Yeah.
Hello, am I audible?
Yes, you are audible.
My question is regarding compressible fluid.
Yes. The voice is lost, it is not coming. Sorry, the voice is not coming. Hmm. 1194.
Hello.
Yeah.
Hello.
Yes.
Sir, it is audible.
Yes, you are audible.
Hello.
Yes.
Hello.
Yes, you are audible.
Hello.
Yes, you are audible.
It is audible, please
Hello.
tell.
Sir, it's 1194 RCIT.
Yeah,
Sir, how the stream function can be defined in the case of 3D incompressible flow?
See, stream function for a 3D, if it has to be defined, it is it. I am giving you the answer.
You tell the answer,
If
How the
yes, I have got the question.
continue, do pore niye nebe.
I have got,
can be defined in the case of 3D incompressible flow?
yes. So if there is a 3D flow, you can think of various planes on which you take the projections of the flow. So instead of taking 3 components of the velocities together, on various planes you can take 2 components of the velocities at a time, and for those 2 components you can artificially define a function, but that will not satisfy the continuity equation. Because that will not satisfy the continuity equation, that cannot be technically called as a stream function. So that can be a pseudo function that can be defined based on 2 velocity components taken at a time, but you can see that for the 3-dimensional flow you cannot define a straightforward function that can satisfy the continuity equation. So some function that cannot satisfy the continuity equation cannot be technically called as a stream function.
Next.
1107. 1020.
Good evening, sir.
Good
Hello?
evening. Good evening.
Hello, sir.
Yeah, hello. Good evening.
Good evening, sir. Sir, my question is, when you said that in turbulent flow, we can have steady state. Means it can, a turbulent flow can also
I have not
satisfy
taught
the conditions
turbulent
of
flow
a steady
yet.
flow. So I just wanted to ask you, by the dye experiment, we can identify the streamlines when we put the dye in a flow.
No, I have not taught the turbulent flow as yet.
Okay, let me answer this question. Yes, look, turbulent flows will be taught in details, but at the present moment, from the knowledge of kinematics, I tell you the answer of your question that in a turbulent flow, in fact, flows are unsteady because turbulent flow at any location, velocities are functions of time, but the unsteadiness is such that it is fluctuating with time over a mean value. You understand? And these fluctuations over a time interval become zero. So therefore, the steady turbulent flow is specified by its mean velocity being independent of time. Okay? So therefore, in turbulent flow, any quantity, all quantities are fluctuating with time. The steady flow is defined to be the flow where the mean quantities, not only the mean velocity, mean pressure, mean temperature, mean density, they are independent of time in spite of the fluctuations. In fact, over the mean values exist in the flow field. Okay, this is precisely the you can define a steady turbulent flow like that.
So one thing I will just request all of you, please try to ask questions based on what we have discussed in today's agenda, because there are certain things which you might have studied from other sources or maybe some books, but it is better to ask questions related to that only after we have completed the corresponding lectures, because otherwise you ask us something, we give you some answer, but you neither you get the full details of the answer nor we make a justification. So to make a justification to the questions, please try to restrict to the questions on the topics for which this particular tutorial session is intended.
When the next session it will be taught, you will be more satisfied.
See, after I
Indeed.
teach you turbulence, this question will not remain in your mind at all, but please wait till that.
Okay, thank you, sir.
1241.
So, sir, can it be possible to generate a streamline, path line, a straight line mathematically for steady and unsteady flow?
Yes, it is.
Why not?
It
For
is very
all
much
flows.
possible. See, these lines are defined for all types of flows.
For unsteady flows, the lines will be different. For steady flows, the lines will be same. Straight lines.
How can it be possible mathematically, sir? Can we make a mathematical equation for that?
Mathematical equations have been told in the class. For path line, the Lagrangian description is the equation for path line. Lagrangian description is the equation of path line. That the locus of a particle, for example, the position vector of a particle is a function of its initial position and time. That means this is precisely the Lagrangian description. That expression is the path line. In one problem we have given the equation of path line. Streamline equation already I have shown. That equation of streamline is derived by what? Velocity vector cross ds. ds means a small differential length along the curve is 0, which reduces to a two-dimensional flow dy dx is equal to v by u. This have been done in the class. This is the equation of streamlines. And straight line equation, which has not been done in the class, can be derived in the similar way, similar way by which we derive the Lagrangian equations, but there tactfully we have to substitute the identified this particle with fixed passing through a fixed point. Fixed point is the specification there. This instead of the particle identity, that is S0 at t is equal to t0. That has to be done and we get the equation of straight line, which has of course not been done.
What we will do is we will post you a worked out problem on
yes.
streamline, streak line and path line tonight.
That I told that a problem will be done,
a
but we will
problem,
post it afterwards.
We will post it tonight. A worked out problem on streamline, streak line, path line.
Streamline and path line, the problem has been solved in the class. We have seen, we have shown you. But the straight line problem we will post it so that you get a better feel.
1022.
Good afternoon, sir. Can you hear me?
Yes, yes.
Yes, yes.
You are extremely audible. Yes.
It's very much audible.
Good afternoon, sir.
Yes, yes.
So my question is, we have studied for psi and phi function, m1 into m2 is we got a negative slope, that is -1.
Yes.
My question is, when we are discussing about the stagnation point,
Yes.
can orthogonality be defined?
No, no, no. As I told that for stagnation point u and v are 0. So it becomes 0 by 0 form. Therefore, this orthogonality does not work for stagnation point. This I clearly mentioned, and you have to keep this in mind that for the psi equal to constant lines and phi equal to constant lines are orthogonal to each other everywhere in the flow field except at the stagnation point.
Okay, thank you, sir.
Okay.
Next.
1218. Bansal.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Good afternoon.
My question is, can a streamline be a closed curve for irrotational flow?
For irrotational flow,
I am repeating the question.
Huh.
Can
Sure.
yes,
streamline be a closed
Sure,
curve
it
for
is
sure.
very much
irrotational
it is very much possible.
Sure.
It is very much possible. I can give you one very simple example. The shape of a body itself is a streamline because there cannot be any flow across a body. Now think about, I gave the same example, that is why I am repeating again. Think about flow past a circular cylinder. Let us say there is a circular cylinder in a flow. So the contour of the circular cylinder is itself a streamline and it is a closed contour.
Another example is that the flow in circular motion, solid body rotation also. The circle itself is the streamline. Good.
1303.
Yeah, good evening, sir.
Good evening.
So my question is there a possibility to get a compressible flow for an incompressible fluid?
Yes, it is possible. It is possible.
Okay. So one more question. Hello, sir.
Yes.
Sir, it is said that in stagnation point, the psi and phi, constant psi and phi lines will not be orthogonal.
Yes.
Why,
Yes.
sir?
The reason for establishing the orthogonality, we had a mathematical expression there where there was division by u and v, and when u and v are 0, it is division by 0, and that division by 0 brings out a singularity at those points. Okay, thank you. One 165.
Good evening, sir.
Good evening.
My question is, what is the concept of stream?
Stream function.
Good evening, sir. My question is, what is the concept of stream filament? And second question is, stream function, can we say that it is a property of fluid or streamline?
Okay, the first question, I think what you mean by stream filament is a stream tube, right? Stream tube is a bunch or a collection of streamlines.
Hello?
Yes.
Hello, sir.
Yes, I am giving you the answer. Yeah. So what you consider as stream filaments, I mean more commonly these are known as stream tubes. Stream tubes are like bundles or envelopes of streamlines.
Yes, sir. Yes, sir.
These are envelopes of streamlines. And what is your next question?
Hello.
Yeah, what is your other question?
Sir, your voice is not audible.
What is your other question?
ছেড়ে দাও next. And other question কি ছিল?
Okay, I will come to your thing later. It is not audible. We will go to a different center. 1075.
Hello.
Hello.
Sir, good evening.
Good evening.
My question is, what is the physical significance of velocity potential function and stream function?
This
practical example of what is
this question I have addressed just now, so I will not repeat any more to save time and get more new questions. Thank you.
ও বলে দিয়েছে প্র্যাকটিক্যাল সব হয়েছে বলা হয়েছে বেশি ভারী না বডি সিটির
1200.
I am from IS College.
Very good.
IS College of Technology, Bhopal.
Okay.
My question is, kindly explain instantaneous streamline and stream tube.
Okay, instantaneous streamline means if you consider an unsteady field, unsteady flow field. So at a given instant of time, at a given location you have particular velocity components, but the velocity components change with time. So when you write the equation of the streamline, dx by u equal to dy by v equal to dz by w, those u, v and w change with time. So at a given time you have a particular value of u, a particular value of v and a particular value of w. Therefore at a given time you have a particular equation of a streamline. That equation of streamline will change as you go to a different time, because at a different time the velocity field will be different for an unsteady flow, and then that in that equation different expressions for different values of u, v and w will be there in that. So at a given instant you may have a particular velocity field, and based on that velocity field you can get a streamline. So streamlines can change from time to time at a given point if it is an unsteady flow. So that is an instantaneous streamline, and regarding the stream tube we have already discussed.
Acha, I will just tell you one thing in this regard, please do not mind if I asked a good question, but please listen to me. Very emphatically it was told a streamline is defined, the very first two words is that at any instant. So therefore the question of instantaneous streamline does not come. Streamline is specified by an instant only. Path lines are specified by the fluid identity. So these are the definitions. These are the characteristic features of the definition. So therefore the map is changing with time obviously.
Okay, 1200. Okay, it is over. 1044. 10.
Sir, good evening, sir.
Good evening.
Sir, good evening, sir.
Good evening.
Hello.
Hello.
Sir, good evening, sir.
Good evening.
Sir, my question is rigid body rotation regarding. Hello.
Yes.
Yes.
Am I audible, sir?
Yes, you are audible.
My question is rigid body rotation. For u equal to minus dou by dou x, u equal to minus dou by dou y, w equal to minus dou by dou z. So what is indicate the negative sign, sir?
See, rigid body rotation means like if you have a particular angle between two line elements that were mutually orthogonal to each other, that is let us say 90 degree, that 90 degree will remain same as 90 degree and it will just rotate like a rigid body.
Hello, you have understood that?
Okay, so one more question. Yes, sir, okay. One more question.
Yes.
Good evening, sir.
Yes, good evening.
Sir, is it possible for us to have a uniform steady flow, sir?
Yes, it is possible. I mean it is very much possible. You can have uniform flow. What is uniformity of a flow? Uniformity of a flow means the velocity field, the velocity components to describe the velocity field, these do not vary with position. So, velocity at a given location, if you say the velocity is same at a different location. Now, that particular velocity itself is not changing with time, that is steady flow. So, steady and uniform combination is a very common combination. So, steadiness means at a given location there is no change with respect to time, and uniform means at a given time there is no change with respect to position.
Hello, just a minute. Let me tell you one thing. I do not know, if you don't mind my impression, whether you are there in the class throughout the day or not. Because the different types, different combinations, uniform steady flow, non-uniform steady flow, uniform unsteady flow, non-uniform unsteady flow examples were given very nicely. And this was given and this was shown in a table. So I think probably some of you are not attending the classes regularly. This question shows like that. Again I am telling that the flow through a pipe of uniform cross-sectional area is a uniform steady flow at a constant rate through a pipe of uniform cross-sectional area. If you disregard in case of highly turbulent flow the variations near the wall, it is almost uniform in the radial direction, and velocity is in a fully developed flow, it is constant in the direction of flow, axial direction. All these examples were given for all sorts of combinations of flow. Then
1044.
বলা উচিত ওটা অ্যান্সার আসছে না, পরে করছে কি এসে কোশ্চেনটা করছে
1044. Oh, 1267.
যখন তুমি ক্লাসে এটা পড়াচ্ছ বলে দিচ্ছ তারপরে কোশ্চেনটা কোনো প্রমাণ হয় না, না তাই মানে কি তাহলে অ্যান্সার ক্লাস করছে না।
Good afternoon.
I would like to you to throw some light to differentiate straight line between streamline.
Well, I mean this was clearly taught by Professor Som in the morning in a very nice way, but if you want to get the definition of streak line and streamline, I can repeat again. Like streamline, at a given instant of time, streamlines are such that the velocity vectors are tangent to those imaginary lines. So, these are streamlines. So, these are imaginary lines. Streak lines means like the locus of all fluid particles which at a previous instant of time all pass through a common point at different instants of time. Okay, next question.
This is the only thing, more than that you cannot take.
1117.
Good evening, sir.
Good evening.
My question is, we are using equation by using two-dimensional incompressible irrotational flow. Why we are not using friction factor or momentum correction factor?
Continuity equation has nothing to do with friction factor. Thinking about friction and thinking about continuity is like comparing apple with orange. Okay. So, you should not relate two unrelated things. So, continuity is conservation of mass, it has nothing to do with friction factor. So, if you have got this concept, this is totally wrong, please get rid of this concept from your mind. Thank you very much. One 1039.
Hello.
Yes. You are not visible.
Hello.
You are not visible. Okay. 1177. One 1177. Audio is not coming. Audio is not coming.
Next.
1299. 1299.
Hello.
Yes.
Yes.
Hello.
Yes.
Myself, Professor R.C. Sharma from Dronacharya College of Engineering, Gurgaon.
Hello.
And good evening, sir.
Good evening.
Good evening, sir.
Good evening.
My question is, we have talked about the Laplace equations,
Yes.
and we normally read Poisson equation and Laplace equation. In the Poisson equation, source density is non-zero.
Yes.
And in Laplace equation, the source density is zero.
Yes.
My question is, what does it mean? And I want specific examples where we use this equation in fluid mechanics.
Beyond this scope.
Okay, fluid mechanics I have already discussed that the stream function and the velocity potential for two dimensional incompressible irrotational flow both satisfy Laplace equation. So, this has been clearly taught. There are examples in fluid mechanics where you have like interfacing of electrostatics with fluid mechanics, that is called as electrokinetics. Do you want to listen to that? I then have to give you a research material presentation.
Pardon, sir.
Yes.
Pardon, sir. I want to know what is the meaning of the source density zero.
I mean,
because second derivative of the potential, streamline potential, second derivative of streamline potential is taken zero.
It is not taken zero. It is proved to be zero. It is. Try to understand one thing. It is not taken to. It is not taken to be zero. It is actually zero. It is not that somebody has just by a wish has taken it to be zero. It has been proved to be zero. Please go through the proofs carefully. Please go through the derivation.
Proved to be zero, but I want the physical meaning of it. What is the physical meaning of it? For streamline flow.
I ask you a question. You tell what is the physical meaning of a differential equation. You first answer this. If you can answer this question, then I will give you answer to your question. What is the physical meaning of a differential equation? If you cannot answer, I will answer, but I expect this answer from you as a teacher. What is the physical meaning of a differential equation? You tell.
Differential equation solve any problem.
No, that is not the physical meaning of a. I am sorry that you have no understanding on differential equation. Okay. Thank you.
Differential equation, second derivative differential equation always solve a problem of the flow.
You have absolutely no understanding on this topic. Please go through the topic and then ask a relevant question. Right. Okay.
Please read the book
carefully. Please read the book carefully.
Please read the book carefully. Read also mathematics carefully. You yourself will be able to know what you are telling. Okay. Thank you.
But my submission is a second del square psi is zero. It is true. Not taken, it's true. I want to know.
Oh, ছেড়ে দাও পাগল হয়ে গেছে মানে এদের পড়ালে তো আমরা পাগল হয়ে যাব ভাই
1174.
Am I mad or are you mad?
Hello, sir.
Napoleon.
Hello.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Good afternoon.
Good afternoon.
Sir, we have a question like, sir, can you tell us the reason for the formation of whirlpool in a water?
So it's the propagation of a pressure wave. It's the propagation of a pressure wave that gives rise to the formation of whirlpools.
Sir, it's a free vortex, so we want to know the reason for the formation of a free vortex. Why the free vortex is forming?
There is no rotationality in the flow. In that particular type of flow, there is no rotation. So I can give you an example. You open the pipeline of a kitchen sink. So you will see that the water is very rapidly attracted towards the pipe. Your V theta is inversely proportional to R. So as you go close and close to the center line of the pipe, you will find that the fluid is being very rapidly attracted by the sink and the water enters into the sink. So V theta is roughly proportional to 1 by R for flow past a kitchen sink, and that is a practical example of a free vortex flow.
Thank you, sir.
1176.
Hello?
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 Yes?
Sir, can you hear me?
Yes, I can hear you.
Hello?
Yes, I can hear you.
Yes, can you hear me?
Yes.
Sir, my question is path line time is same for all particles for constant velocity? Second question is path line.
No, your first question itself is not a valid question. Your first question is itself not a valid question. Please frame it properly. There is nothing called as path line time. There is nothing.
Listen my question once again. Is path line time is same for all particles for constant velocity?
Path line, there is nothing called as path line time. At time equal to 0, you start tracking a particle and see how the particle is evolving with time. That is, find the locus of the particle. So, at different time it will be the position of the particle will be different. So, there is nothing technically called as path line time. This is a wrong terminology.
Secondly, what is the physical significance of the phi and psi?
I have told it at least 3-4 times, and during this question and answer session itself I have discussed about this. So, I will not go through that again to save time and to get new questions. 1316.
Hello.
Hello.
Hello, sir. My question is, suppose a party is moving in a flow field and we are expressing this motion by Lagrangian, in the Lagrangian form. Suppose it reaches a particular station, particular point, where it has its motion expression by Lagrangian. We want to express it in the Eulerian form. What actually criteria we have taken to relate this Lagrangian motion with the Eulerian?
Okay. Okay. So, I will request you please get back to the derivation of acceleration of flow which was derived by Professor Som. So, if you think about the definition of acceleration, in the definition of acceleration you will see that the total change in velocity is some total change in velocity because of the change of velocity at a given time plus change in velocity at a given location due to change in time plus change in velocity due to the change in position. So, in deriving the change in velocity due to change in position, we took a limit as delta t tends to 0. This is very important, and in the limit as delta t tends to 0, you have the fluid particle at a given location. That identified fluid particle corresponds to even an Eulerian description. So, in the limit as delta t tends to 0, Lagrangian and Eulerian descriptions merge. That means, the fluid particle which has been identified at a given location, whatever is its velocity, the same velocity is the velocity at that point. So, velocity at a point is the velocity of a fluid particle which at that instant is passing through that point. That is where the Eulerian and Lagrangian descriptions merge. 1256.
Hello, sir. Good evening, sir. My question is, from the morning session by the sir, if velocity changes with respect to, if velocity won't change with respect to space, that is considered as a uniform flow, and if velocity won't change with respect to time, that is considered as a steady flow.
Steady flow. Yes.
But if I take an example as a why the velocity is changing because of the change in space. But if I take the steady flow, I mean unsteady flow causes, if I take an example by which
Answering this question, in the morning session I explained that. But you have to pose the problem in a correct way. For example, if you consider a flow through a converging channel, first of all a steady flow. How do you visualize a steady flow through a converging channel in practice? When the flow rate of flow through the channel is kept constant. The rate at which the flow enters the channel goes out at the same rate. So this is a steady flow. What does it give? The velocity at any location, for example, the center line velocity. At any radial location, I consider the center line velocity. That changes, increases in the direction of the flow. But at any location, axial location, the center line velocity remains invariant with time because the flow is maintained steady. The inlet and outlet is maintained steady. This is a flow at a steady rate, but the flow velocity changes because of the converging section, which has been told by Professor Suman Chakraborty, discussed in the continuity equation, how the velocity changes. So this is a non-uniform but steady flow. But you can superimpose with this non-uniformity and unsteadiness if you go on varying the flow at the inlet. You understand? If go on varying the flow at the inlet, then at any instant the velocity will be such an instant to instant, at any location rather, the velocity will go on changing with time. You understand?
Yes, sir. So, by your answer, I conclude that if mass increases with respect to time, that may cause.
Not increases, the rate of flow is changing with time. In any pattern, the rate of flow may change with time. In any pattern, so therefore the velocity will change. That means you forcefully change the velocity. Okay? By changing the inlet flow, varying with time. Okay? Then you can superimpose unsteadiness with the non-uniformity.
Okay.
1256. Okay. 1161. 1161.
Hello.
Yes.
Can you hear me?
Yes.
Now my question is, can you differentiate the Lagrangian and Euler approach in the form of behavior of particles? Behavior of particles, how to differentiate these two approaches?
See, I mean your question needs to be correctly posed, but like nevertheless, I mean I think we are repeating this answer, but let us repeat once more. Lagrangian means you are following a particle and finding out its locus. Eulerian means you are focusing your attention on a specific location rather than on a specific particle. So you are as if you are sitting with a camera, numerous particles are coming in that region and numerous particles are going away from that region. You are not tracking those individual particles, but you are assessing the motion at that location as the particles are coming in and going out. Okay, thank you. 1068.
Hello.
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 Is it audible, sir?
Yes.
Hello. Is it audible, sir?
Yes, it is audible.
Well, my first question is that why there is negative sign in the velocity component of stream function?
I told you repeatedly that your stream function should be defined in such a way that it satisfies the continuity equation. So if you take u equal to del psi del y, and if you do not take v equal to minus del psi del x but plus del psi del x, then del u del x plus del v del y will not be equal to 0. So you have to satisfy the continuity equation. So if one velocity component if you take plus, the other velocity component you have to take minus, so that when those are substituted in the continuity equation, they should satisfy the continuity equation.
Okay, and so my second question is that when we talk about the conservation of mass, the amount of mass entering should be equal to the mass leaving.
That is only
but
at
the derivation of continuity. Yeah, but in the derivation of continuity, what you have taken that mass entering is m dot x, but mass leaving is m dot x plus del x.
See,
why is that so? Why it is not
whatever
identical?
mass is entering is same as the whatever mass leaving only when it is steady state.
Okay.
But sir, if we are talking about the conservation of mass, then what amount of mass is entering, that should be equal to the volume. That is m dot x only.
Yes, I can't. I mean, please repeat your question.
Yes, sure. My question is, if m dot x is the entering mass
Yes.
in any control volume, so the leaving mass should be m dot x only. Why it is m dot x plus del x?
Your concept is not correct, because that is only a special case. I have given you an example. Let us say you have a tank. You supply some gas to the tank and some gas leaves the tank. Let us say some gas enters the tank at a rate of 10 kg per second and some gas leaves the tank at the rate of 1 kg per second. So, the remaining gas, what it will do? It will accumulate mass within the tank, and it will actually, the gas in the tank will be more compressed to accommodate that extra gas.
Okay, okay, okay.
জিজ্ঞেস করেছিল নিজেই জানে না কিন্তু
1064
x plus delta x
ঘুমোচ্ছে সব বসে দেখে।
না এখানে হচ্ছে কিছু লোক আসেনি ক্লাস করেনি
1178 You are not audible. One 1171.
Hello.
Yes.
Hello.
Yes.
Continuity equation for heat and energy and heat is del U by del T plus del Q is equal to 0. How it is derived from continuity equation, sir?
Continuity equation for heat, there is nothing called as continuity equation for heat. Let me ask you a question, from which book you have learnt it? Because that book should be banned from the market. First thing should be done is that book should be banned from the market.
The word continuity equation means the conservation of mass. The word continuity does not go with the heat. There is no continuity of heat. There is a continuity of heat flux in heat transfer at the interface that is entirely different, but there is no continuity of heat. It's probably trying to tell the first
1223.
Hello sir, good evening sir.
Good evening.
My question is, the continuity equation which you have derived,
Yes.
del U upon del x plus del V upon del y plus del W upon del z is equal to 0. This is the differential form. The another form, the mathematical is equal to A into V. That is the constant. So what is the difference? Can you elaborate?
See, as I told you, the differential equation is valid at a point. So, when you are writing the differential equation, you are writing the relationship between density, velocity and their derivatives at a point. Now, when you are writing the integral equation, you are not writing it at a point, you are writing it over a section. So, when you are writing, let us say A1 V1 equal to A2 V2, then that V1 is not the velocity at the point 1, that V1 is the average velocity over the section 1. Only when the velocity profile over the section is uniform, then the average velocity is same as velocity at a point. So, the integral equation, to summarize, the integral equation is valid over an integral domain or over an area, whereas the differential equation is valid at a point.
Okay sir, धन्यवाद.
Okay. 1193.
Sir, our question is, while deriving equation for rate of volumetric strain,
Yes.
some higher order terms were neglected.
Yes.
To what extent this will affect our the accuracy of our solutions?
Okay, because Professor Som derived this.
Look, if you go through my note, correctly it is seen from mathematics. If you derive the volumetric strain rate, the volumetric strain rate is defined as 1 by V dV dt. That means the rate of change of volume per unit volume, which was derived from the change in volume, okay, from an element divided by delta t, limit of that when delta t tends to 0. That is the definition. If the change in volume is delta V, you see my class note, delta V, okay, and this change in volume takes place for a fluid element to traverse from one point to another location and takes delta t time. So this delta V by delta t, limit delta t tends to 0 is the volumetric strain rate. Now when we replace delta V in terms of the velocity gradient into the delta t, 1 plus del u del x into delta t, 1 plus del v del y delta t, you see that in that expansion you will see there will be term containing delta t, no question of neglecting. When you take the limit of all those terms, delta t tends to 0, this automatically becomes 0 because all these terms contain either delta t square, delta t3 or delta t and higher power of delta t. So when delta t tends to 0, by simple limit analysis it was made 0. So no question of neglecting, it is identically 0 from mathematical concept. So therefore limit delta V by delta t, 1 by V delta V by delta t as delta t tends to 0, which is equal to 1 by V dV dt, is automatically del u del x plus del v del y plus del w del z. Okay, it is mathematically 0 by the concept of limit. Okay.
1312. 1312. You are not audible.
Sir, good evening, sir.
Good evening.
We are from DMA College of Engineering 1312.
Okay.
Sir, if I am not wrong, I have only one question. You have mentioned that in stream function, the equation of continuity is dou u by dou x plus dou v by dou y is equal to 0.
Yes.
Here, psi is the stream function. So, dou psi by dou y is equal to u, dou psi by dou x is equal to v.
Minus dou psi by dou x, not plus dou psi by dou x, minus dou psi by dou x.
Okay, sir. But it is just a reverse case in the case of velocity function. Is it the assumption, sir?
No, 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 it is not an assumption. Velocity potential, let us recall, velocity potential, when is it defined? Can you remember it? It is defined for irrotational flow only. So for irrotational flow, what is the definition of irrotational flow? Curl of the velocity vector or vorticity is 0. So if the curl of the velocity is a null vector, that means if curl of a vector is a null vector, then that vector can be expressed as a gradient of a scalar function. This is from vector calculus. So instead of v you can write grad of phi. So if you write the x and y and z components, you will get u equal to del phi del x, v equal to del phi del y and w equal to del phi del z. So it is from the condition of irrotational flow. Okay.
Thank you, sir. Thank you.
Okay. 1122.
Sir, my question is, what is the difference between two approaches of conservation of mass equation and which is more accurate?
No, both approaches are the same. One approach is called as control mass approach, another approach is called as control volume approach. The two approaches that I have used for deriving the continuity equation, the first approach where we have taken an identified mass and then we have applied the conservation of that mass, that is called as control mass approach. Control mass is a particular system of particles of fixed mass and identity, that is called as control mass, and so it is following Lagrangian approach. Control volume approach on the other hand is a fixed volume of space across which we are writing the mass balance. So that is an Eulerian approach. So the two approaches of mass balance or conservation of mass that I have discussed, the first approach is Lagrangian approach and the second approach is the Eulerian approach. One, three, three, four.
Good evening, sir.
Good evening.
Hello.
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 Yes.
Difference between stream function and velocity.
Hello. So,
My question is that is there any physical or practical approach to understand the terms such as streamline, streak line, path line, and vorticity?
Yes, like in a let me give you a physical way of understanding a streak line. All of you have agarbatti, right? You use the agarbatti for like worshipping gods or goddesses. So, like the visualization of flow, that what you see above the agarbatti, these are illuminated by particles which at a given instant of time, at different instants of time, have passed through the tip of the agarbatti. So, or if you inject a dye, colored dye at a point in a flow field, let us say that you inject a colored dye. So, after a given time you will see that there is a colored line in the flow. How do you get this colored line? This colored line you get because at different earlier instants of time a particular colored dye material passed through a given point and you are seeing the locus of those points. So, that line is a streak line. Now, in a steady flow that line will be same as path line or streamline, but in flow visualization always remember that in flow visualization what we fundamentally see is not streamline or path line, what we see fundamentally is streak line. If the flow is steady, then the path line, streak line and streamline are the same, but all this was covered by Professor Soon.
And this example was given by dye injection. It proves that many students are not attending classes. I am sorry to say they are coming only at the question session, question asking session to ask question, because this example that flow visualization is given in the class, and it was also told in a transient flow where the three lines are different, how can we get the lines? There are instruments which captures the particle displacement from where we get the history. All these things were described in details in the session, morning session. I am really sorry that flow injection, everything.
1248.
It's a good thing that we can make a conclusion.
1248.
Clear.
My question is, while we are studying FlowNet, can you hear me?
Yes.
Hello.
Yes. Yes.
Sir, my question is, while we are studying FlowNet, which flow we consider, whether turbulent flow or laminar flow?
I mean, first of all, what is the relationship between flow net and laminar or turbulent flow? Let us discuss about turbulent flow and then you come back to this question.
Do you know what is turbulent flow? Flow net is
1011.
Question
it is
last question. Unnecessary.
Hello.
Hello.
Hello, sir.
Hello.
Hello, sir.
Hello.
Hello.
Yes.
Hello, sir.
Yes, you are audible. Just go ahead.
Hello. Hello.
1216.
ছেড়ে দেওয়া
একটা লাস্ট
এরা শিফট ডিউটি করছে, মানে কিছু আসছে কোশ্চেন করার জন্য।
1250
ক্লাস অ্যাটেন্ড করছে না।
1250.
Hello.
Yes.
Hello, sir. Am I audible?
Yes, you are audible.
Am I audible, sir?
Yes, you are audible.
Sir, my question is, at what condition we may expect to have a rotational motion? Does it have anything to do with the viscosity and rate of angular deformation?
Yes, I will give you an example in another lecture to illustrate that an original rotational flow, irrotational flow may become rotational because of viscous effects. Let me give you an example. This is a very common example, nothing to do with fluid flow, but let us say you are moving in a bus. You are there in a bus and the bus is coming close to the bus stoppage. When the bus is coming close to the bus stoppage, you want to come out of the bus and you are in a hurry, so you want to come out of the bus before the bus stops. So what you do is that you have got your foot in contact with the ground before the bus has stopped, and the ground is suddenly trying to come to bring you to a standstill, but you have already your inertia that is trying to drive you forward. So you will have a tendency to topple. So many people who are smart enough, they will actually run in the forward direction to maintain their inertia while they are coming out of a running bus, otherwise they may fall because of this rotational effect, and this rotational effect is induced by the ground which tries to prevent your motion, whereas your inertia is trying to make you move forward. So in a very similar way, viscous effect tries to make you slow down and your inertia tries to bring you move forward, and because of the viscous effect the tendency of forward motion is prevented, and that brings a rotational effect. So if there is an irrotational flow, because of viscous effects, rotational effects in the flow may be brought in. I think this is the last question that we are taking today, and we are already running out of time, and we close the session today.
Hello sir.
Yes.
Last question. Okay.
Okay. Last question. Last question. Okay.
Sir, at first day we have discussed the selection of volume of continuum. The graph of rho against T.
Yes.
It was having erratic behavior at the start.
Yes.
Then it is at constant.
Yes.
It is upward inclined.
Yes.
Sir, I was not able to get that. What is the basic fundamental?
Okay. Let me repeat that. So if you now when you choose a volume to calculate the density, how do you calculate the density? So you know the mass within that volume, you divide that mass by the volume, but question is how large or how small the volume should be. If the volume is too small, then what happens? Now these molecules are always in random motion. So if the volume is too small, the number of molecules in the volume will also be very small, and then there can be a very serious error if we have uncertainties with regard to the occupancy of even one or two molecules. Let us say that the volume has only 2 molecules. So if out of those 2 molecules, one molecule out of its random motion goes out of the volume, then there is an error of 1 molecule for like 2 molecules. So there is a 50% error. So this kind of error is there because there is insufficient number of molecules if the volume is considered to be very small. On the other hand, if the volume is considered to be very large, then what happens? You do not capture local point to point variation in the density, you only consider an average density over a large volume. So in reality you have to make a compromise. You should not take the volume so small that local fluctuations will come into the picture, but you should not take the volume too large also where point to point variation is lost and you get a gross density. So you have to take a volume element in between where you get a stable value of the density that does not fluctuate too much over small scales, at the same time it covers point to point variation,
and which is characterized by Knudsen number.
Okay. So I think we stop our session today.
Yes.
And it has been a long day, and please take a good night's rest, and we will meet again tomorrow morning when we discuss about dynamics of viscous flow in viscid flows. Thank you very much.